Hi guys, welcome to the practical lecture of Principal Component Analysis with Python's machine learning library Scikit-learn. In the previous lecture, we have discussed the key concepts and working principle behind PCA. It's time to learn by doing. As always, the code notebook is provided in the course material. Let's use the breast cancer dataset for this section. As we have learned, principal component analysis is a great statistical tool to reduce the dimensionality of the dataset without losing information when our dataset contains several dimensions or features. Breast cancer data is a great example for PCA. We can load this dataset directly from Scikit-learn. So let's start with new notebook and import some important libraries like NumPy, Pandas, Seaborn, and Matplotlib for visualizations. And then we are going to set Matplotlib inline so that we can see the plots within Jupyter Notebook. So import NumPy as np, import Pandas as pd, import matplot. We can use tab to autocomplete pyplot as plt, and then import Seaborn as SNS. And now we can set matplotlib as inline. Now we can load the dataset from sklearn dot datasets. We are looking for breast cancer data. We can get this dataset in cancer underscore data. Now we have the dataset in cancer underscore data object. Cancer underscore data is a dictionary-like object, and we can access keys using dot keys method here. So we see we have data, target values, target names, description on the data, and feature names. We can check how many features we have. We can simply use length on cancer data, and we can pass in the column feature name. So we have 30 features. So this is a good data for PCA. Let's create a data frame df, data frame, and we pass in the data and columns name cancer data features name. So we have our data frame df, which is ready now. So we can check the head of the data frame, and here it is. We got the data in df, and we see that we have all the features as columns in this data frame. Note that we did not really get target values appended with this data frame because we are in principal component analysis is a part of unsupervised learning, and we don't need the target values. Another important thing to note, it is not easy to visualize high dimensional data. If you recall the theory lecture, to plot each feature against the other in a simple 2D scatter plot, we need 435 such plots for a dataset with 30 features. And you know we can calculate this number using the formula given in those slides. Furthermore, the important thing is we may not get any useful information from those scatter plots. So for this high dimensional data, Let's use principal component analysis to find out the first two principal components and plot the data in two-dimensional feature space. To move forward, data scaling is another important thing. We need to scale our data so that each feature has a single unit variance. Luckily, Scikit-learn has a built-in method for data scaling. So we need to import standard scaler from Scikit-learn to scale our dataset. So let's import that one from sklearn. It is in pre-processing import standard scaler. Let's create its instance now. We can call this instance as a scaler, standard scaler. So we have created an instance for standard scaler. Let's now fit the scaler to the data and then transform the dataset to the scaled data. We can use scalar.fit on our data frame, and then we got the scalar fitted to our data frame. And the next step is to use this fitted scalar to transform the data frame into scaled features. This object, the df scaled, will get the scalar transform what we are going to transform our data frame. So now we have the scaled features in df underscore scaled. So we have done the pre-processing. Everything is in standard scale now. Now the data is ready for principal component analysis. Similar to all other models, we need to create an instance, pass in number of components we want, fit the data, and then instead of predictions, we need to do transformation here. Everything will be done on pre-processed scaled data, which is in df underscore scaled. To do all this processing, we need to import PCA from Scikit-learn. It's kind of decomposing the data into its components. So it is in a decomposition class in Scikit-learn. From sklearn dot decomposition import PCA. Let's create its instance with small PCA and pass in the components we want. So we want two components from our data. So we want two principal components of this data with 30 features. So we pass the n components equal to 2, which says that we want two principal components of our data which has 30 features. The next step is PCA to fit our data, which is actually scaled data. So we got the fitted data. Now we can transform data using this PCA, which is fitted on scaled data, and then we can get PC1, 2, two components, principal component 1 and 2, PCA dot transform our scaled data, and then we have principal components in PC12. PC12 is a NumPy array. Let's check the type of this thing first. So this is NumPy ND array. So let's create a data frame df PCA pt dot data frame. We can pass in data as PC12, and we can pass in columns, which is a list PC1 principal component 1 and PC2. So Let's check the head of the PCA. So now we have these two principal components. So our all data is represented by these two principal components, PC1 and PC2. Let's check this head. This is quite long. So the principal component 1 and principal component 2 is a representation of our data into two principal components using PCA techniques. If we check the information or info PCA dot info, we have PC1 and PC2 569 entries and there is no null value. So we have reduced our data with 30 dimensions to just two principal components, principal component 1 PC1 and PC2. We are lucky that we have a target class here. So just to distinguish the target values, we can simply pass in C as a target value. We can plot a scatter plot here, PLT, create a figure. We can pass in figure size, fig size equal to say 10:8, and then PLT scatter. X is our DF PCA PC1 and Y is our DF PCA PC2, second principal component. So we said we can pass in C because luckily we have C and we can get that C from cancer data, which is actually target. So how it looks like. Oh, this is kind of black and white. Let's pass in another parameter here, CMap, so that it looks little better. Let's see, set1. So now we have two classes, two separate classes in red and gray color. We can print the labels as well. I hope you remember all this from your matplotlib lecture. So now we have PC1 and PC2 along X and Y axis, and these two components are representing the whole data in this plot. Now, instead of 30 features with only two components, the data can be easily separated into its target classes. This is the power of PCA. The next step is components interpretation. We already learned in the lecture that it is not a trivial task to understand what these components represent. However, PCA has great power of dimensionality reduction. The components do not relate one-on-one to each other. They actually correspond to combination of all original features. The components themselves are stored as an attribute of the fitted PCA object. We can get the components using PCA.components. PCA.components. So each row in this NumPy metric array represents a principal component, and each column relates back to the original features. Let's convert this NumPy array into pandas data frame and visualize the relationship with a heat map. We will pass the columns from our original dataset again. So df underscore PCA, we can say component, so that we don't mix with the data frames, pd dot data frame, pass in the data as components, and then we can get the columns from our original dataset columns, which is in feature names, and then let's display the head of our dataset. The data frame has two rows, 0 index for principal component 1 and its relationship to each of 30 features in the original dataset. Similarly, index 1 for principal component 2 and its relationship to each of those 30 features in the original dataset. Let's have a look on another plot, a heat map showing the relationship of principal component to the features in the dataset. We can use Seaborn's ability to plot heat map here. So plt.figure, let's set the fig size again equal to 12.6 maybe, and then SNS dot heat map, pass in the data PCA component, and then set CMap, say rainbow. The heat map visually shows the relationship of the principal component to the respective feature. Higher the value is, more correlated the feature is to the principal component. This is what these components represent, the combination of all the original features in the dataset. We can also see which feature is more important to the respective principal component. So, using principal component analysis, we have reduced the dimensionality of our dataset to two components or two features, PC1 and PC2. We can use this reduced data in df_PCA and apply or use logistic regression or any other classification algorithm to see how the classification algorithm work on this reduced set of features. Let's feed in the reduced data from PCA into a logistic regression. So the first thing we need to do here is to separate the data into X and Y. So we have X equal to dfPCA, and we have to pass in the target values which we can get from our original dataset to Y. Now we need to import train test split from model selection, and we can use shift tab to copy this long line so that we don't need to write it again. And let's run this cell. Something went wrong, so yes, now it's working. Let's set this test size equal to 30 and leave the random state as 42. So as we said, we are going to use logistic regression model, so we need to import this logistic regression, and if you remember, this is a part of linear regression model. So let's create its instance log R, and then repeat the process what we used to do in our model fitting. So fit the log R to our train data. Let's do the predictions. Log R dot predict. So what is our prediction, which is on test data? This is unseen data to the model. So now we have predictions from our model in predictions. So now let's import classification report and confusion matrix, and then see how these two looks like. We can print classification report, pass in the test values what we have the original one, and then pass in the predictions. Then we can print confusion matrix, pass in the test values and predictions, and let's run this cell. So this looks quite good actually. The logistic regression model actually performed very well on the principal components. The results here are much better than those we got in the logistic regression section. However, please note that we only used 14 features in the logistic regression section, whereas we have used all 30 features in our principal component analysis. Hence, the component PC1 and PC2 are actually the representation of all the 30 features in the dataset. So rather than using 30 features, we can get two principal components using PCA and use those two components to train our model for the classification problem. That is the power of PCA. I hope you enjoyed this lecture and got a very good understanding of PCA. This information will be very useful whenever you will be dealing with the data with higher number of features or dimensions. Now you know the power of principal component analysis. See you in the next lecture with the project on PCA. Good luck.